This is video 14. In this video we describe the different interactions between a path and a window. We start by some basic definitions. Firstly, consider a window W. Here, this window is a simple B-infinite path. We do not consider that the window is a cycle. In this example, the window is in gray and its direction is from the left side to the right side. Consider the cut of the grid G1 and G2 associated to W. We remind that the graph G1 is the left side of the window and that the graph G2 is the right side of the window. Secondly, consider a path P. We consider that the length of P is at least 2 and that its first and last positions belong to the window W. In this example, the path P is hatched. Since the first and last positions of the path P belong to the window, there exists two indices I3 and I4 such that the position WI3 is the first position of the path P and the position WI4 is the last position of the path P. In this example, I3 is equal to 28 and I4 is equal to 32. In this example, I3 is less than I4. In this case, the segment of the window W associated to the path P is the segment of the window W which starts at index I3 and ends at index I4. In our example, this segment is hatched and the path P is in white. If I3 is larger than I4, the segment of the window W associated to the path P is the segment of the window W which starts at index I4 and ends at index I3. We consider the path P again. Now there exists two indices I1 and I2 such that I1 is the smallest index I such that the position of the window W at index I is also a position of the path P, and I2 is largest index I such that the position of the window W at index I is a position of the path P. We say that P starts in WI1 and ends in WI2. Note that the index I1 is always lower than the index I2. The width of the path P is defined as I2 minus I1. In our example, the path P starts in W9 and ends in W113. Its width is 104. As a side note, we consider two different paths, the window W and the path P. Here the letter I is used for the indices of the window W, while the letter J is used for the indices of the path P to avoid confusion. Now we consider two indices J1 and J2 such that the position of the path P at index J1 is the position of the window W at index I1. Moreover, the position of the path P at index J2 is the position of the window W at index I2. Intuitively, these two indices represent where the path P reaches the positions where it starts and ends in the window W. If J1 is strictly less than J2, then the path P is positive, and if J2 is strictly less than J1, then the path P is negative. Here we consider paths of width at least 1. We postpone the definition of a negative or positive path of width 0 to the next video. In this example, the index J1 is equal to 8 and the index J2 is equal to 63. Then our example is a positive path. A positive path P is extreme if and only if the index J1 is equal to 1 and the index J2 is equal to the size of P. Intuitively, the first position of a positive extremum path is where the path starts in the window W and its last position is where it ends. In our example, the path P is not extremum. A negative path P is extremum if and only if the index J2 is equal to 1 and the index J1 is equal to the size of P. We can always extract an extremum path from any path. If the path P is positive, then the extremum path extracted from it is the segment of P from index J1 to index J2. In our example, we represent this segment in hashed while P is in white. This segment starts at index 9 and ends at index 63. Here we represent only the path Q, which is the extremum path extracted from the previous path P. Of course, Q is extremum. Now we say that a path P is basic if and only if the intersection between this path and the segment of the window W associated to it is made of only the first and last positions of the path P. In our current example, the path Q starts in W9 and ends in W113. the path Q intersects with the segment of the window W associated to it at the position W24, then the path Q is not basic. Let's go back to the previous path P. This path is basic. Now, we consider a path A such that this path is a subgraph of the graph G2. In this case, the path A is an arc of G2. Along the videos, we will denote arcs by using the letter A. Remark that in our example, the arc A starts in W28 and ends in W104. Its last position is W101 and then the arc A is not extremum. Moreover, it intersects with the window W at position W66. Thus the arc A is not basic. Here we have an arc which is never basic nor extremum. Consider another arc A of G2. In this new example, A is basic, but the arc A is not extremum. Here we have an example of a basic arc which is not extremum. Consider this new arc A. Here this arc is extremum, but it is not basic. Here we have an example of an extremum arc which is not basic. Finally, consider this last example. In this case the arc A is extremum and basic. We say that this arc is elementary. An elementary arc intersects with the window W only at its first and last positions. In fact, a basic and extremum path is always an elementary arc. Now we will use the different kinds of paths to characterize different parts of the grid. We consider the extremum path Q introduced before. Since the first time that the path Q intersects with the window W is also the first position of Q, and since the last time that Q intersects with the window W is also the last position of the path Q, then we can define a new simple B, infinite path W prime. This new path is the concatenation of three paths: the segment of the window W from -infinity to I1, the path Q, and the segment of the window W from I2 to +infinity. We represent this new path in gray. Note that the direction of this path depends only on the direction of W. The path W prime can be used as a window to define a new cut of the grid which is G3 and G4. In the general case, there are no dependencies between the first cut of the grid and this new cut of the grid. Let's go back to the previous basic path P. Consider the segment S of the window associated to the path P. Since the path P is basic, then the concatenation of S and P is a simple cycle. Then this finite cycle can be used as a window called W prime. This window is represented in gray. Note that the direction of the window W prime depends on the direction of path S and thus on the direction of window W. It does not depend on the direction of path P. Consider now the interior of this new window. This graph is called the interior of the basic path P. In this example, the interior of P is hashed and is neither a subgraph of G1 nor of G2. Consider now an extremum arc A of G1. We want to define the interior of A, but here the arc A is not basic and thus we have to proceed differently. We represent here in hatched the graph G1. The arc A is a subgraph of this graph. Now we draw in gray the window W prime associated to the extremum arc A. We consider the cut of the grid G3G4 associated to W prime. In this example, we have drawn a window W in white and G4 in hashed. Remark that the window W is a subgraph of G4 which is the right side of the window W prime. In this case G3 is subgraph of G1 and G2 is a subgraph of G4. We define now the interior of A as the intersection of G1 and G4. This graph is finite. If A is elementary, then this definition of interior is coherent with the previous one and that it is possible to define the window of this graph. If A is not basic, then it is not possible to define the window of this graph. Nevertheless, if a path starts inside the interior of A and leaves it, then neither this path contains a position of A or an edge of G2. Also note that the segment of the window W associated to the arc A is a subgraph of the interior of A. The last remark is very important to study the interactions between different arcs. Consider our window W and its cut of the grid. Consider the extremum arc A introduced before. This arc starts in W-2 and ends in W79. Now consider the positions W20 and W109. Remark that 20 is larger than -2 but it is also less than 79. Then the position W20 belongs to the segment of the window W associated to the arc A and thus it belongs to the interior of A, whereas the position W109 does not belongs to the interior of the arc A. Then any path starting in W20 and ending in W109 either intersects with arc A or contains an edge of the graph G2. Thus any arc of G1 passing by W20 and W109 intersects with the arc A. Consider now a special case where the window is obtained by the extension of a good path of direction V in period P. In our example, the vector V is 6, 4 and the period is 22. Consider an arc A of G1 which starts in W14 and ends in W43. Then the width of A is 29. The width of this arc is greater than the period of the window. Thus the translation of the arc A by -V would start in W-8 and ends in W21. Remark that the translation of A by -V is also an arc of G1. Thus A and A-V intersect. If we draw A-V, we can see this intersection. Thus any arc whose width is larger than the period of the window intersects with its translation by -V. This remark will be fundamental to prove the J lemma. Let's go back to the previous window W and to the extremum arc A. Now consider an arc A' which starts after W-2 and ends before W79. In our example, the arc A' starts in W19 and ends in W31. We say that the arc A dominates the arc A'. If this arc does not intersect with the arc A, then it is a subgraph of the interior of A. Now consider another arc A' of G1. In our example, the arc A' starts after 79 and we say that arc A' is consecutive to arc A. If the index I3 is strictly larger than the index I2, we say that A' is strictly consecutive to A. To summarize, there are only three possible interactions between two arcs A and A' of G1, either they intersect, either one dominates the other one or one is consecutive to the other one. We now introduce decomposition. A decomposition is a sequence of arcs A numbered from 1 to L. Moreover, all these arcs are extremum and any arcs of this sequence is consecutive to the previous arc of the sequence. In this example, consider an extremum arc A1. Consider another extremum arc A2 which is consecutive to A1. Consider another extremum arc A3 which is consecutive to A2. We have here a decomposition of length 3. The decomposition of the window W associated to a decomposition is a sequence of segments of the window W called SI which are numbered from 1 to L. The segment SI of this sequence is the segment of the window associated to the arc AI. We have drawn here the three segments of the window W associated to the previous decomposition. Now the dual decomposition of the window W is another sequence of segment DI of the window W numbered from 0 to L. The segment DI of this sequence starts where SI ends and ends where SI plus 1 starts. From this definition the dual segments D0 and DL are infinite while the others ones are infinite. The dual segment E0 is indexed from -infinity to 0. Note that the union of all the segments of the window W and all the dual segments of the window W is the window W. Also note that there are L plus 1 dual segments of the window W. Finally, we can extend the definition of the window associated to an extremum path to a decomposition of several extremum arcs. In this cases, we create a new window which is the concatenation of the dual segments with the arcs of the decomposition. We obtain this new window W' which is the concatenation of two L plus 1 segments. The cut of the grid associated to this new window W' is called G3 and G4. As previously mentioned, G3 is a subgraph of G1 and G2 is a subgraph of G4. Intuitively, G3 is obtained by removing all the interiors of the different arcs from G1.